ethers and epoxides, aldehydes and ketones. So we're all but finished with aldehydes and ketones. What I thought we would do today to start us off is maybe begin with a mechanism problem. So I'll put one up on this slide here. It's actually one of the 3 that I gave you on that supplemental mechanism practice worksheet last time. So I thought we could go through it together. So I don't know if some of you may have had a chance to try it out, others may not have. But what I'll do is just go ahead and draw it up, and then you can try your hand at it. I'll give you 5 minutes or so to work on it. You can talk amongst each other. Obviously, it's not an exam. So, and then we can go through it together. So this is the 3rd problem from that mechanism practice. Okay. So take about 5 minutes and see what you can come up with for this mechanism, and then we can go over it as a group. how are we doing with this one?
Halfway.
Yeah?
I don't know.
Did y'all want to go over it? Or did you want another minute or so?
I'm ready.
All right. Well, then let's go ahead. Okay. Go ahead and, before I forget, start recording this. Okay, so looking at the reaction, there's a couple things that we should notice off the bat. Number one, we're obviously breaking the ring open, so that's one very apparent thing here. The other thing is that in the reactant, we have no oxygen. In the product, we do have an oxygen. So that means you've got to be getting oxygen from somewhere, right? The only place you really have an option of getting oxygen into this molecule is from your reagents. So what this is telling us is that at some point during the mechanism, water is going to have to attack this thing, okay? So those are kind of the broad strokes of this mechanism at the outset. Really the only thing that we can do to start this is do something with the proton. That's really our only option. Another kind of clue that I would give you is that when you have a catalyst, be it acid or base, use it in the first step always. If the reaction were to progress without the catalyst, then why would you add the catalyst? So if you have a catalyst present, use it in the first step of your mechanism always, all right? So with that, I think the most logical thing to do, in this case, given the reagents that we have, is have the nitrogen with its lone pair attack the proton. Give us something that looks like this. So you might, at this stage, you might not really know where to go next. If you ever encounter something like that where you're kind of stuck in a mechanism, what I would recommend you do is draw resonance structures. Sometimes that can really be a help in terms of kind of pointing you in the right direction. So if I were to draw the resonance form of this structure, we get something like that. So basically all I did was I gave the pi electrons to the nitrogen, all right, which put the positive charge on the carbon. And this should make some pretty decent sense to you because of the two resonance forms. I mean, both of them are positively charged resonance forms. However, the nitrogen is less happy bearing a positive charge than the carbon is. Right? Nitrogen is much more electronegative than carbon, and so it is going to be much more unhappy with a positive charge. So that said, this would be expected to be a fairly prominent contributor to the overall picture of the species. Once we have that, it would make sense. Remember, we talked about having to get water in this molecule at some point. Well, now we have a positive charge. We know water is a nucleophile, so it would make sense to have H2O to come in at this stage and attack there. All right, so what I'm going to do now is my little shortcut, because I'm a little bit lazy most of the time, and so I'm just going to write minus H plus. And that should get us to a neutral intermediate in this mechanism. So now, at this stage, again, we've incorporated the oxygen into the molecule, which is good. This is one of the things we said we had to do at the outset. One of the other things we said that we had to do at the outset was break the ring open. Which means something is going to have to leave. Which means we need to have a good leaving group. So what can we do at this point to try to get to a good leaving group?
What do you need the hydroxide?
Yeah, we're going to protonate something. If you protonate the OH group though, aren't you just going to be going backwards in the mechanism?
Never mind.
So I mean, that's a good option. You know, we see that all the time when we're trying to make good leaving groups. I mean, we've done it countless times. Make a good leaving group, protonate an OH, turn it into water. However, in this particular mechanism, I don't know how much good that would do us because like I said, if you protonate the OH group, we're just going backwards.
Well, the nitrogen has its own pair back because you broke the bond.
Yep, exactly. So maybe instead of protonating the oxygen, we could think about protonating the nitrogen. So that is a good leaving group. In the same way that when you protonate a hydroxyl group, it turns it into a good leaving group. If you protonate an NH, it is also going to make a good leaving group. All right? So maybe at this stage we could think of breaking the ring. This. All we have to do now is a minus H plus step again. That gives us the neutral aldehyde. And that's pretty much the product. The only difference, if you look at how we drew the mechanism originally compared to what we have at this stage, is we protonated the nitrogen and the amine, because if you're under acidic conditions, amines will naturally protonate. Okay, but that is essentially the end of the mechanism. Does anybody have questions on this, on any of these steps?
Professor,
Mhm.
so we have to use the double arrows because it's an acid catalyzed mechanism?
No, but just because it's an equilibrium.
Okay.
The entire reaction is at equilibrium in the same way that the acetal formation is at equilibrium. You know, you can put the acetal on, you can take the acetal off. A lot of these addition reactions involving the weaker nucleophiles are going to be in equilibrium. However, if you were doing a mechanism on an exam and you had put just regular arrows through all of this, I wouldn't get angry about it.
Okay.
But yeah, I mean, it's just more correct to put them at equilibrium.
Okay.
Any other questions on the mechanism?
So the last step would just be to have the nitrogen's lone pair go grab another hydrogen.
Mm-hmm.
Okay.
Yep. All right. So what was this mechanism, by the way? We didn't look at this specifically in lecture, but we saw a version of it.
That's the E-mine?
Yeah. This is just, so what we looked at in lecture together was the reverse of this process, right? We looked at imine formation in lecture. This is the reverse of what we looked at in lecture. This is imine hydrolysis. Okay. Any other questions on this?
Can you roll it up?
Hmm?
Since they finished, we just have to make sure.
Is it NH2 what, sorry?
If our product is NH3 at the end?
Oh, yeah, so if you have an amine in the presence of acid, it's just gonna naturally pick up the proton. This is a simple proton transfer acid-base type step, because amines are basic. This guy, under acidic conditions, is gonna just go grab a proton.
The H you drew, coming from the carbonyl,
Mhm.
that was just already there, you just drew it in. Is that right?
Well, because what we had, to make the carbonyl, we started with this, those lone pairs came in, so that's the double bond created by those electrons pushing in, and.
But that carbon already had that hydrogen, you just hadn't
Yeah,
brought
yeah,
it
yeah,
in before.
yeah.
Okay,
Yeah,
so it's not like
because-
it just appeared, it just,
Right.
was
So
already
if you-
there.
If you think about it, just to kind of draw it out explicitly, there's an H there.
so it's just there.
And so, yeah, it's been there the whole time.
Okay, that's what I thought.
All right. Any other questions on this one? Okay, if not, then why don't we go ahead and look at the beginning of Unit 3. So Unit 3 is going to begin with carbon 13 NMR. And so I have the slides for the C-13 NMR on Canvas. Those might be helpful to have as we start going through some of this, because especially once we start diving into the spectra, you'll probably want to have them close by. So I'm going to switch over to the slides in just a second, but I did want to mention, you have all been exposed to NMR at this point. You had proton NMR. You probably spent a good chunk of time last semester learning proton NMR. And I think I have some good news for you. So for those of you who are like me and really struggled learning proton NMR, C-13 is a walk in the park. It is much, much, much less complicated than proton NMR. And so whereas you probably last semester spent a good, I don't know, I'm guessing 3 to 4 lectures learning proton NMR, we're going to get it done in probably 1. So we'll spend the rest of today talking about C-13, and then maybe a little bit into Wednesday, or no, not Wednesday, it's your exam, but a little bit of Monday's lecture, finishing up C-13. But that's the only time we're going to spend on it. It's that simplified that you need less than half the time to cover it. So that should be a little bit of comfort at least. So I'm going to go ahead and switch over to the slides. Okay, so a lot of the stuff that you learned for proton NMR can be directly applied to C-13. The fundamentals are the same, all right? So when we talk about nuclear magnetic resonance, remember, only certain nuclei are NMR active. And to be NMR active, if you remember, one of two things has to be satisfied, and that is you either need so they must have spin, and the reason, or the way nuclei acquire spin is they must have either an odd mass number or atomic number. Okay, so for instance, go back to proton. Proton, what we're looking at is H1. So its atomic number is 1, its mass number is 1. Both of them odd, so proton are NMR active nuclei. And that's a really good thing for us, because if you think about I mean, not every isotope, is present in the same percentages, but H1 makes up well over 99% of all naturally occurring hydrogen. And so you have the vast majority of H's out there in the world that are NMR active, right? So that's why you can take any sample, dissolve it in your whatever NMR solvent you're using, throw it in the instrument, and take anywhere from 1 to 4 scans, and you usually get a very nice, usable NMR spectrum. Okay? Compare that to carbon. So carbon exists in a few different isotopes, the most abundant of which is carbon-12. So it has an atomic number of 6, a mass number of 12. What's the problem there? Yeah, both of them are even. So carbon-12 is not NMR active. Okay. Well, what about its heavier isotope? The heavier isotope still has atomic number 6 because it's carbon, but because it has an additional neutron, its mass number is 13. Well, that's odd, and thus that is the NMR active nucleus. But there's a bit of a problem with that. If you look at the relative amounts of carbon-12 versus carbon-13, carbon-12 is approximately 98.9% abundance, carbon-13 only 1.1%. That is not ideal, because only about 1% of all of the carbons in your molecules are actually going to be giving a signal in the NMR. And so what this leads to is a fairly dramatic difference in the sensitivity. So what we can say is C-13 NMR is nowhere near as sensitive as proton. So whereas when you're trying to get a proton NMR, you typically dissolved your sample in the deuterochloroform, threw it in the instrument, scanned it 1 to 4 times, and out popped a really nice, pretty proton NMR spectrum. You are not going to be able to do that for C-13. So the way we fix that is in one of two ways. You either need very, very concentrated samples, or more commonly, you take many more scans. So kind of and it's going to depend on the specific sample, on how much material you have, but I would say on average, most people, when they go to collect a C-13 spectrum, kind of the magic number is about 96. So this is one of the reasons why we are not going to have you go take C-13 spectra of your compounds in lab. Because you can imagine how time consuming it would be to get everyone through the NMR having to collect 96 scans on every compound. Okay? So it's just a little bit too time consuming to do in a practical sense. But in terms of the overall process of NMR, it's going to be this exact same thing for carbon that it was for protons. Meaning, normally, if you have a collection of molecules, the nuclei, assuming they have spin, those spins are just kind of randomly aligned. They're spinning in random directions. However, once you put that sample of molecules into an external field, external magnetic field, so that's what this is trying to represent here. That red arrow is representing the magnetic field exerted by the NMR instrument. Remember, the NMR instrument is nothing more than a giant magnet. Right? If you think about how you collect your NMR samples, you put it in the tube, you you put it in the spinner and you hit inject and it drops down. Well, it's dropping down into a gigantic magnet, right? That's that external field that you see represented by this red arrow. And so whenever you place a sample of molecules into this strong external field, what happens is all of those nuclei, their spins will align. And they can align in one of two ways. They align either with the magnetic field. This is what we term the alpha spin state, and you can see the spin is the same direction as the external magnetic field. Or they align against the magnetic field, what we consider the beta spin state, and you can see this one here is going in the opposite direction of the external field supplied by the magnet. All right? And these are not of the same energy, right? As you can see depicted in the illustration, the alpha spin state is a lower energy than the beta spin state. And so they are separated by some energy gap. And this delta E is going to differ depending on the electronic environment of the various carbon atoms. Okay? And so what the instrument then does is it supplies a radio frequency pulse. All right? And so if that radio frequency pulse happens to exactly match this difference in energy, then it will induce a spin flip. And we say that those nuclei are in resonance. Okay? But not just any amount of energy will be absorbed, right? That the amount of energy absorbed must perfectly match this energy gap between the alpha and beta spin states in order to be absorbed. Right? Everything at the molecular level is quantized. All right? So, what we're going to do now, before we move on, does anybody have questions about that? Okay, so what we're going to do now is just kind of go through and look at some various aspects of carbon-13 NMR that are different from proton NMR. And the first one we're going to look at is chemical shift. So the thing to remember here is that the same things that affected chemical shift in proton NMR will affect chemical shift in carbon NMR. All right, so, and what that's gonna primarily be is things like electronegative atoms, right? So you know that whenever you have an oxygen or a halogen or something like that attached to your molecule, those protons were shifted further downfield than say just regular alkyl type protons. It's gonna be the same thing with carbon. If you have electronegative atoms attached, so this slide is a little bit busy, and you certainly don't need to memorize it. I would just kind of keep it as reference because it's more of a comprehensive list of functional groups. But you can see it has a lot of stuff that we never worked with. When was the last time you worked with a sulfoxide or a sulfone? Never. Nobody cares about that. So this is the one that I would learn. It's kind of a simplified version of what we just saw. But what you'll note is that if you have just regular alkane type carbons, those appear the farthest upfield. So the way I kind of like to think about these is I think about my alkyl type carbons being in the, I would say 0 to 40 range. And then you've got your carbons that have electronegative atoms. So like oxygens or nitrogens or halogens, things like that. Those are going to tend to appear in the, I would say, 50 to 90 part per million range. All right, by the way, what you can see from this slide is notice where our scale goes out to. It's a very different chemical shift scale than what we saw for protons. And that has everything to do with the fact that this delta E for carbons is very different than the delta E for protons. So if you think back when we were looking at chemical shifts of proton NMR, we typically use 0 represented by TMS, and we looked out to about 12 on the part per million scale. As we just saw, that scale for carbon is very, very different. So we're still going to use 0 represented by TMS. We're still using the same units, namely that part per million scale. It's just the scale goes out much, much further, and we typically measure out to about 220 parts per million. The other things that can cause de-shielding in the C-13 spectrum is double bonds. And this shouldn't surprise you. Double bonds cause de-shielding in proton NMR as well. Think about those vinylic and aromatic protons in proton NMR. If they were vinylic, they tended to appear somewhere between 5 and 6. If they were aromatic, 7 to 8. So the aromatic and vinylic protons are significantly de-shielded, as are the aromatic and vinylic carbons. So if you, and they tend to be, just kind of rough approximation, between 100 and 150. So that's where we're going to find the carbons that are on double bonds. Once we get out beyond 150, really the only type of carbons that appear out there are carbonyls. And we can subdivide that a little bit further. So I would say 150 to 200, that's where you're going to find carbonyls attached to heteroatoms. So what would that look like? Well, that's going to be kind of your functional groups, things like carboxylic acids, esters, amides, what else do we have out there? Anhydrides. Okay. So any kind of a carbonyl functional group that has some sort of a heteroatom attached. And then we get to the farthest downfield, the 200 and above. These are also going to be carbonyls, but they are going to be the carbonyls specifically of aldehydes and ketones. All right. Any questions there?
I'm sorry, what was the last one? Is it hydrogens?
Oh, this one down here?
Yes.
Anhydrides. So as a general rule, you can kind of approximate where carbons are going to be based on where their corresponding protons appear. So as a general rule of thumb, what you can do is you can say that a carbon will be about 15 times where its corresponding proton appears. Okay, so for instance, if we were to say, do a couple of examples. Let's say we had something like butane. Well, those methylene protons should appear, if you think back to your 420 shifts. Methylene protons of an alkyl chain are typically about 1.2 part per million. So this carbon that bears those protons, we would expect to be about 15 times the value of the chemical shift of its protons. So if my math is right, I think that's about 18. So that alkyl methylene carbon, we would expect about 18 part per million. But what if we had acetone? Well, remember, those protons of acetone are somewhat de-shielded due to their proximity to the carbonyl group. And so, those chemical shift values, I would think, expect those methyl protons to be approximately 2.1. So we say 15 times 2.1. We would expect that carbon of the methyl group to be somewhere around, I'm just gonna call it somewhere close to 30. All right. Any questions there on the difference in the chemical shift relative protons relative to carbons? All right. One of the other things that we saw when we were looking at proton NMR was this concept of splitting, or what we call multiplicity. So you recall, let me just put up a fairly simple molecule. Let's say we had this, and we were going to look at the proton NMR. What kind of peak would I expect to see for the terminal methyl group? So remember when we talk about multiplicity, we're talking about the singlet, doublet, triplet, etc. So what kind of peak would these protons of the methyl group be represented by?
Triplet.
Yeah, it'd be a triplet, right? We're kind of governed by the n+1 rule. So we go to the nearest neighbor. So this methyl group has 2 neighbors. 2 plus 1 is 3. So we would expect this to be a triplet. What about this methylene group here? What kind of peak would that be? Yeah, you've got 3 neighbors to the left. You've got 2 neighbors to the right. That's 5. 5 plus 1 is 6. So we would expect it as a sextet. And then finally, you've got this methylene that's closest to the carbonyl. It doesn't have any neighbors to the right, but it's got 2 neighbors to the left. 2 plus 1 is 3. It would also be a triplet. Okay? So remember, that's how we handled multiplicity in proton NMR. In carbon, multiplicity is a little bit different. I'm gonna draw this one. So when we're looking at carbon NMR, we do have to at least initially consider the possibility that you could have carbons splitting other carbons. But in order for that to occur, remember, C12 is NMR invisible. So nothing's gonna happen if you've got carbon 12s. So the only way you're gonna get splitting of carbons by other carbons is if you have C13 next to C13, next to C13, next to C13. So what is the likelihood of that happening? And we could calculate it, right? 1% of all carbons are C13, so that would be 0.01 times 0.01 times 0.01 times 0.01. Not very likely. I mean, in an Avogadro's number worth of molecules in a given sample, yeah, it's gonna happen. But it happens so rarely, it is not detected at the NMR scale. All right? So we don't have to worry about carbons splitting other carbons. So we can say that there's no carbon-to-carbon splitting. Or there is, we just don't see it because of the very limited number of C-13 atoms in the universe. But what we do also have to consider is protons can split carbons. And the biggest one of these is, it's gonna, again, gonna be a little bit different. The biggest type of carbon to proton splitting is not by nearest neighbors. It's actually by the protons directly attached to carbons, right? This is what we call 1J coupling. 1J coupling, that's referring to one bond coupling. So when I say a one bond coupling, so if we're looking at this methyl group here, the biggest the biggest effect of splitting is going to be of the hydrogens on this carbon that are directly attached, that are one bond away. Right, that's this 1J represents. Coupling that is one bond away. And this is very large coupling constant. Typically between 125 and 300 hertz. So remember when we talk about a coupling constant, that is the distance between peaks of a multiplet. So for instance, if you had a triplet, when I talk about a coupling constant, I'm talking about that distance. The distance between the peaks of the triplet. Okay? So if we're thinking about 1J coupling alone, we're still going to use the n+1 rule. We're just, instead of using the neighboring protons, we're using the protons directly attached. So let's think about 1J coupling on the molecule that we've been working with. How would this carbon be represented if it were coupled to its protons? It would. So it's got 3 protons directly attached. 3 + 1 is 4. So this would appear as a quartet. The next one over, the CH2 group here, it's got 2 protons directly attached. 2 + 1 is 3. This would appear as a triplet. Same thing with the next one. This one is CH2. 2 protons directly attached. 2 + 1 is 3. It would also appear as a triplet. So a potentially complicating feature here is that you don't just get coupling from the protons directly attached. That is certainly the largest coupling constants. But you do also get coupling of the carbon from neighboring protons as well, what we call 2J coupling. Mm-hmm.
Even if the neighbor carbon isn't a C-13?
Yeah, because the protons are still H1.
Okay.
So the protons are still NMR active nuclei. So this 2J coupling is going to have much smaller coupling constants. And you could see how this could get potentially complicated, right? So if we're saying that the biggest coupling is from the directly attached protons, but then you also get smaller coupling from neighboring protons, imagine what that methyl group, that terminal methyl group is going to look like. Right? So it would be kind of a widely spaced quartet, but each of those, think about your splitting tree, remember those that you did last semester? So you'd have a widely spaced quartet, and each of the 4 peaks of the quartet would be split because the neighboring protons are 2, 2 plus 1 is 3. You'd have a widely spaced quartet, each of those 4 peaks split as a triplet. So it would look something like that. You would have a quartet of triplets. So you can see how this could get potentially quite complex. You know, maybe not in a structure as small as the one we're dealing with here, that has only 4 carbons and, what, 7 hydrogens. But imagine if your molecules start to get to be bigger, 10 carbons, 15 carbons, 20 carbons with associated protons. Your spectra are going to get quite ugly and complicated. And so, fortunately, nobody does carbon NMR that way. We will always do some form of what we call decoupling. And there's a couple ways that you can do this. When we say decoupling, what I mean is we're uncoupling the carbons from their protons. Okay, there's a couple ways you can do this. The first of which is what's called off-resonance decoupling. And this simply removes the 2J coupling.
Is it actually like breaking the bonds?
No, it's done with a radio frequency. So it sends a radio frequency pulse that corresponds to the frequency of the neighboring protons. So kind of representing that delta E of those neighboring protons. And it sends a radio frequency pulse causing them to be in resonance. So they're constantly flipping back and forth and back and forth and back and forth, and that essentially eliminates their signal in the NMR.
So essentially it's just muting them, it's not destroying the molecule.
Exactly.
Okay.
Yeah. So this would take this, if we do an off-resonance decoupling, it would take this quartet of triplets and simply make it a quartet. So the only thing that is splitting are the protons directly attached to the carbon. All right. So that's one way we can do this. And so I think I have a spectrum to show you. So this would be an example of off-resonance decoupling. So let's see if we can take a minute looking at this spectrum and see if we can identify which carbon is giving which signal. So we can do that in one of 2 ways with this. There's kind of 2 important pieces of information looking at this structure and comparing it to the spectrum. And number 1 is obviously the splitting pattern. Number 2 is the chemical shift. Remember, the same things affecting chemical shift in proton NMR are going to affect chemical shift in carbon NMR. So let's just start, we'll go downfield to upfield. What do we think this peak, which carbon is this peak representing? Yeah, I think so. I think this has got to be letter D. Number 1, letter D should be the most D-shielded because it's directly bonded to the electronegative oxygen. All right, so chemical shift wise, that makes sense. What about splitting wise? Does its multiplicity make sense? Letter D has 1 attached proton, 1 plus 1, N plus 1 would be 2. Well, it should appear as a doublet, which it does. What's the triplet here? Let's see. Yeah. It's gotta be, just based on its chemical shift, it's gotta be either one of those carbons directly attached to, or sorry, not directly attached, but we'll call beta to the hydroxyl. Right? Either B or C are gonna be the next most deshielded carbon atom, because they're the next closest to the electronegative oxygen. So then we can use the splitting to kind of help figure out which one, right? This one has 3 directly attached protons. So 3 plus 1 is 4. This should appear as a quartet. This one has 2 directly attached protons. 2 plus 1 is 3. That letter C here, that should appear as a triplet, which this does. So I think it's safe to say that this triplet is letter C. All right. You kind of already, well, the quartet, that has to be a methyl group. So basically, that quartet could be letter B or letter A. Which do you think that quartet is? Yeah, it's gotta be B. Because this methyl group is a whole lot closer to the electronegative atom than that methyl group. So this should be further downfield than that. So I think it would be safe to say that this is your letter B methyl group. This is your letter A methyl group. All right. Any questions on that?
Is there a reason for the B carbon to have like a higher integration than A carbon at all, or is that just sort of like that error?
Let me see, just, so that's D, what do we call this one? C, and this one was B, and that was A.
It's just
Okay,
like-
so which one?
Which one? They're different sizes, but
Mm.
should have the same relative importance.
We're gonna get to that in just a minute. The short answer is, no, there is no reason. Integration in C-13 NMR is very, it fluctuates quite a bit, and I'll give it away. The short answer is we don't integrate carbon peaks. So that's another one of the simplifying factors in C-13 NMR is there's no integration because it's not consistent. So yeah, I don't know
There's
why.
no-
Yeah, there's really no rhyme or reason in predicting integration in C-13 NMR. Okay, any questions on how we identify those peaks in the off-resonance decoupled spectrum?
So why is, B pushed, up further than C, I mean, pushed lower than C?
That's a good question. So why is it, if you look at the two carbon groups, letter B and compared to letter C, they're both the same distance away from the electronegative oxygen. So why is it that letter C is more deshielded than letter B?
Yeah, CH3 group?
Mm-hmm. Yep. The way you're gonna see, if you're talking about equivalent peaks, so kind of in the same location, what you're gonna see is that, what do we call these guys? Methine. So something that has no hydrogens on it, a quaternary carbon, we call it, those are gonna be the most deshielded. Something that has just one hydrogen would be next. Something that has two hydrogens is next, and then methyl groups are the least deshielded. And there's a good reason for that. Think of the difference in electronegativity of a carbon relative to a hydrogen. So if you look at an electronegativity table, a carbon has an electronegativity of 2.5. A carbon has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.1. So simply put, a carbon is more electronegative than a hydrogen is. So the more carbons you have relative to hydrogens, the more de-shielded the peak is going to be. So the fact that in this molecule we're comparing a methylene, a CH2, to a methyl, CH3, the methylene has more carbons on it, so it would be more de-shielded than a methyl group. Okay? Any questions on that? Okay, so this is what we call off-resonance decoupling. The other way that we can do this is what's called broadband decoupling. Broadband decoupling simply removes all coupling. As a result, everything appears as a singlet. Every unique carbon peak in the molecule is simply a singlet peak. And by far, if you look at any carbon-13 spectra out in the real world or published data or whatever, broadband decoupling is, I would say, the way that 90% of all C-13 spectra are done. All right? Any questions there? So let's have a look at what that would end up looking like. So we already saw the off-resonance decoupled spectrum. So that's what we just saw. Comparing that to the broadband decoupled spectrum, that's what you get. So you can see all of those peaks just collapsed down to singlet peaks. All right. Okay, this goes. The other thing, the last thing I wanted to mention to you was something that we were just talking about, and that was integration. And as I mentioned a minute ago, there is none in C-13 spectrum. We don't integrate the peaks. Right, so when it comes to comparing carbon to proton NMR, as I said at the outset, C-13 spectra is a heck of a lot simpler than proton. And so just kind of to summarize here, the 4 key differences. First and foremost, the sensitivity. Due to the low relative natural abundance of carbon-13 in the universe, carbon-13 is much, much less sensitive than proton. And as I said a minute earlier, to address that, you either need very concentrated samples and or many, many more scans. Secondly, due to that difference in that energy gap between the alpha and beta spin states of carbon relative to hydrogen, the scale is much, much different. So as we saw, a proton NMR, you're typically looking at from 0 TMS out to 12 part per million. With carbon, you're still looking from 0 TMS, but it's out to 220 part per million. The third one is in the coupling or the splitting. All carbon spectra will be to some degree decoupled, usually broadband decoupled, to where all of your peaks collapse to singlets. And then finally, integration. There is none for carbon spectrum. All right. Any questions on that, on the differences between carbon and proton NMR?
I was just gonna ask, like, so I guess with proton NMR, you're able to identify more like structured features, but with carbon NMR, really only limited functional groups, right? In that sense.
Yeah, functional groups and also the number of environments, the number of specific type of carbons. But, as you probably started to figure out, we never characterize using one method alone. You're never gonna have an unknown molecule, or you're never gonna, try to do a reaction and figure out what your product is by just getting an IR, or just looking at a UV spectrum, or even just looking at a proton NMR. We always have at least two ways of characterizing and making sure that those two things corroborate. If you want to publish, if you've been doing some research and you come up with a new compound that's never been made before, in order to publish that compound as a new chemical entity, you have to have 4 methods of characterization. Proton NMR, carbon NMR are the kind of the 2 that are required, and then 2 others, like perhaps high resolution mass spectrometry. That's very common as a 3rd, and then the 4th, some people use IR, some people use elemental analysis, some people use, there are various other kind of the 4th way. But yeah, you have to have multiple methods of analysis to prove the structure of a new chemical entity. So C-13 is the same way. You're never gonna just be given a carbon-13 spectrum and say, what is this compound? It's always gonna be C-13 in conjunction with something else, at least one other thing. So it's a piece of the puzzle. So let's go through, speaking of chemical environments, and see if you can predict how many carbon peaks we would expect to see in these 2 molecules. So take a minute and see if you can do that, and we'll look at it together. So how many do we think for that first one?
6.
Yeah, let's see, I think that's right. 1 there, 2, 3, these two would be equivalent. And then those two would be equivalent. And then, oops. Okay. So, yeah, 1, 2, 3, 4, 5, 6. So I think we would see 6 distinct peaks for that. What about for the next one?
Okay.
1, 2, 3, 4, and then yeah, the 2 methyls of the isopropyl would be equivalent. So I think we would see 5 there. All right. So I think I have the 2 spectra to show you. So if you look at this one, initially what we see is 1, 2, 3, 4, 5. That doesn't quite add up. So this is the reason why it only looks like 5 peaks is because this is a computer generated spectrum. You know, if you were gonna take this spectrum experimentally, you would not process your data in this way, because it's a really stupid way of processing the data. Because from 200 to 60 is nothing but dead space. There's nothing there. So it makes no sense to have this blown up that large. Instead, what you would really do is you would expand this region of the spectrum where your peaks are. You see how you've got this very, very bold peak right there? It's a lot darker than the rest. That's because that's actually 2 overlapping peaks, which you would actually be able to see if this spectrum were not so condensed. You know, if this were expanded out to the region of interest, you would see that this is actually 2 separate peaks, not one really dark one. Okay? So this does have 6 peaks. It's just because this is a computer generated spectrum, it's hard to make it out. As far as distinguishing which one is which, I mean, I think there's really only 2 that I would feel comfortable trying to pick out of this. And that has to do with the question we were just talking about in terms of carbons being more electronegative than hydrogens. So what we had said was quaternary carbons are more deshielded than tertiary, than secondary, than primary. So on that basis, I would think that this should be the most deshielded, and that the most shielded. But all the rest of them are just CH2 groups and a big alkyl thing, which would be very, very difficult to distinguish between each other. All right? Any questions there?
So what you were saying before is that it has less to do with the number of hydrogens attached and more to do with the fact that because it has hydrogens, it's not attached to as many carbons.
Yep.
Okay.
Yeah, carbons being more electronegative than hydrogen, the more carbons you have attached, the more deshielded it's going to be.
Okay, that makes sense.
All right, what about this one? We said we were expecting 5, and I think that's what we have. 1, 2, 3, 4, 5. All right, so that's good. Do we think we could figure out which one is which? I'm just going to give these letters, and then we can go through and see if we can assign them. I'll go first. This one has got to be C. Right. That is very apparent because the only thing that shows up in that very, very deshielded 200 range and above are the carbonyls of aldehydes and ketones. What's gonna be the next most de-shielded? That 140. Yeah, it's gotta be either B or D, because those are the two next closest to the carbonyl. But if you look at the difference, this goes back to what we've been talking about. B is a CH2, D is a CH. D has more carbons attached, so it should be more de-shielded. So once you've got that, I guess it makes sense that B would go next. The methyls of E are about the same distance as the methyl of A. So that'd be hard to choose. I would not take that bet. Some people might be tempted to say, well, you know, E is representing two methyl groups, A is only one methyl, so the bigger peak should be E. Maybe, but I would not put money on that. Remember, we do not integrate carbon peaks. All right, let's look at a couple more. So in this, we have another carbonyl. So I think it's safe to say that the one over 200 is going to be letter B. What's the next most de-shielded?
C? No, E.
E.
Yeah, I think it's gonna be E. Remember, A and C are both next to something that's de-shielding. Letter E is directly bonded to something that's de-shielding. All right, so once we've done that one, then A and C would be the next most, and I guess the CH2 is gonna be more de-shielded than a CH3, so it would make sense for this one to be C, and this one to be A. And then the most upfield signal is gonna be the one farthest from all the de-shielding stuff, namely letter D. Any questions on that one? All right, let's look at this one. This one is the first one we've seen with a benzene in. A, B, C, D. So let's handle the benzene carbons first. I think I could safely say one of the four benzene carbons. Which one do we know for sure?
Being the most de-shielded?
Mm-hmm.
A.
Yeah, A is gonna be the most de-shielded because it is a quaternary carbon. That's another feature of quaternary carbons, by the way, that is fairly notable. Not only are they more de-shielded, but they are also short peaks. So if you look at the four different aromatic carbons, you've got these guys that are all kind of the same size, and then you've got this one that's really short and really de-shielded. So I would feel comfortable saying that that's gonna be the carbon letter A. As far as the rest of them, I got no clue. I'm just gonna call that mess the other three, B through D. What do you think is, so we've handled all the aromatic ones now. What do you think the next most de-shielded is gonna be? Yeah, I think it's H. It's the one that's directly bonded to the electronegative oxygen. Then, the benzene rings are also somewhat de-shielding. So I think it would make sense that the next one is gonna be the one bonded to the benzene. What's more de-shielded, G or F?
G.
Yeah, it's gotta be G. Because F is only beta to the ring, it's very far from the oxygen, whereas G is beta to the oxygen and it's also beta to the ring.
And it has more carbons attached to it too.
Yeah, and it has more carbons attached, right. Okay, any questions on this one?
So if the same rules apply that like it's a 1/5 of, say if it was a Cl on, instead of the OH, is the same rule that the beta gets like 1/5 of that, or?
Yeah, roughly. You could, yeah, you can use that same kind of 1/5 rule for carbons as well. Okay, let's do this one and then I think that'll be a good place to stop. So, as a general rule, the way I usually handle these is, as we've done with the rest of them, I usually like to start downfield and just work my way up. So if you look at the downfield portion of this, in that 100 to 150 range, we just have the 2 peaks. So that would strongly suggest a double bond, which we do have. Let's take B, C, D, E. First off, let's count peaks first. We've got 1, 2, 3, 4, 5, 6. Does that make sense? Why do we have 6 peaks in this and not 5?
Because it can't rotate the geminal.
Yeah, exactly. Look at the methyl groups. The methyl groups are not equivalent. In this case, because you have a double bond here, remember double bonds don't freely rotate. And due to the restriction of bond rotation between here, A and F are not the same. Right? For instance, A is always going to be trans to the ethyl group. F is always going to be cis to the ethyl group, and they cannot interconvert. So A and F are actually different carbons. They're in different environments. So that's why we have 6 peaks and not 5. Which of the 2 double bonds, the double bond carbons, is the furthest downfield?
B.
Yep, it's gotta be B. Not only is it bonded to more carbons, but you'll notice that it's a short peak, which would suggest it's quaternary. So that would make the other double bond carbon here. What's next? The next most de-shielded has got to be one of the ones that's allylic, meaning A, F, or D. Yeah, it's got to be D. D is a CH2 versus the 2 different methyl groups. So then it's got, the next 2 are going to have to be A and F. Which one is which? Well, your guess is as good as mine. I don't know. But the most upfield would be letter E. All right. Any questions on this one?
So you said that for one of the double bond carbons short? I'm not sure I understand.
Oh, letter B is a quaternary carbon, meaning it has no hydrogens attached.
Right, okay.
And so those peaks, those carbons that have no hydrogens tend to be shorter than other peaks.
Just height-wise?
Yeah.
Okay.
And that's what you can see here. Between those two similar peaks, there's a very, very big difference in peak height. And that is also another clue on how you can kind of figure out carbons that are in similar environments. Right, these are both vinylic carbons, but they're very, very different in peak height. And that would suggest that that's probably a quaternary carbon. Okay? Okay, then I think that's probably a good place to stop. All right, so why don't we do what we did last time? So last time